I'm going to use this video to review the homework on continuity and intermediate value theorem. And so if you're in my class, this is in your packet, and you should have done problems 1 through 9, and hopefully you're using this video to support your understanding rather than just trying to look and get hints from my work. I'd rather you try it yourself first. So in problem number 1, you have a piecewise function, and it's comprised of 3 pieces. You have a quadratic, you have another quadratic, and you have a horizontal line y equal to 4. So the first thing is to sketch a graph of f of x, and of course this is a prerequisite skill, and in class we've spent some time talking about the best way and the easiest way to sketch that graph. And so down here in number 1 you see the red graph is the piece of x squared to the left and including x equal to 1. So when x is 1, y is 1. So you get a portion of that parabola. Now for the second piece, I am going to remind you to graph that parabola. It probably is helpful to know where the vertex of that parabola occurs. So if you think back to the quadratic formula and you take the first part, the negative b over 2a, this gives you the x coordinate of the vertex of the parabola. The plus and the minus simply move you to the right-hand root, and to the left-hand root, but that's a longer discussion that we can have in class. So if I do negative b over 2a, or the opposite of b over 2a, I should say, so I'll have the opposite of negative 2, which is positive 2, over 2 times 1, which is 2, and 2 divided by 2 is 1. So that tells me the x coordinate of the vertex is 1. And to get the y coordinate, I'm going to substitute that into the function itself. So that'll give me 1 minus 2 is negative 1, minus 1 is negative 2. So the vertex of the parabola lies at 1, negative 2, and because there's no equal to on that, that inequality, that's going to be an open circle, and that's where I got that piece right there. And then I'm going to substitute the x value of 3 and get the corresponding y value. I'm going to put an open circle there, and I know that it's quadratic, so I have some idea of what that shape looks like. And then the third piece, this is the equation y equal to 4. So I'm going to graph the horizontal line, or technically a horizontal ray, beginning at 3 and traveling to the right. So you can see my graph below of what the sketch of the piecewise function should look like. Letter B, determine all values of x where the function f of x, the piecewise function, is not continuous, and use the definition of continuity to explain why f of x is not continuous at those values. So we clearly and easily see that there is a discontinuity at x equal to 1. So I'm going to say f of x is not continuous at x equal to 1, and I'm going to state very carefully and mathematically my reasoning. The limit as x approaches 1 of f of x does not exist. In other words, remember the 3 conditions of continuity is, for your brain, is that there has to be a y value produced, and we do have a y value here, and the limit has to exist, and that's where things fall apart for us here. But if the limit did exist, we know that the limit has to equal the y value, and that's the third condition of continuity. All right, our second place where this function, this piecewise, is not continuous is here at x equal to 3. It is a jump discontinuity, but that's not the question. We're going to simply state why the function is not continuous, and again, it's because the limit as x approaches 3 of f of x does not exist. So that has to be written very mathematically. All right, let's clear the board here. Let's go back to a little bit of Algebra 1. The next question is, what is the domain of this piecewise function? And the domain is from negative infinity to infinity, meaning all real numbers, but I'd prefer you to use interval notation. That means all values of x produce a value of y, even at the discontinuities. So for example, back up here, at x equal to 1, there is a y value produced, and at x equal to 3, there is a y value produced. So all values of x produce a y value, therefore the domain is from negative infinity to infinity. In letter D, we're going to decide whether the intermediate value theorem applies to the given interval. If yes, give the conclusion of the theorem? If no, explain why. So we have two given intervals here. So the first given interval is from -3 to 1. So let me clear the board and start this again so you can see. So from -3 to 1, so -3 is right here, and 1 is right here. So remember, the condition of the intermediate value theorem is that, first of all, we have to have a function that is continuous on the given closed interval. All right, so from -3, which is somewhere up here, the graph continues to travel upward, but in this interval, the function is continuous on a closed interval. All right, the second part of the theorem is that we need to know the y values of our endpoints, so we're going to need to know f of -3, and we're going to need to know f of 1, and we can find those simply by substitution. We already know that f of 1 is 1, and f of -3, if you substitute -3 into y equal to x squared right here, you get -3 squared, which is 9. So that is the y value. That is the y value for produced at -3. All right, so come down here and take a look at my write-up. The intermediate value theorem applies to f of x on the closed interval from -3 to 1 because f of x is continuous, and notice I specify the specific closed interval. Therefore, there is a value c, that's a value of x, such that, and this is a mistake, this should be +1, such that all of the y values between +1 and +9 are included. You have to pass through every y value from 1 to 9. So there's an x value that generates those particular y values. All right, let's go back to our second. Let's clear these annotations, and let's go to the second interval. And the second interval begins at 1, which is here, to 3, which is here. So now we can see that on this interval, the function is not continuous on the closed interval because the function is not continuous at the endpoints. We have open circles on those particular pieces of the function. So the intermediate value theorem does not apply because f of x is not continuous on the closed interval from 1 to 3. Number 2, a toy car travels on a straight path. During the time interval from 0 to 60 seconds, the toy car's velocity, v, measured in feet per second, is a continuous function. So that's important that we know that we have a continuous function on the closed interval from 0 to 60. Selected values are given below. For the interval from 0 to 60, must there be a time, so there's our question right there, must there be a time when the velocity of the car, toy's car, is -2 feet per second justified? All right, so we already know that we have met our condition of being continuous, function being continuous on the closed interval from 0 to 60. All right, all is good there. Then we need to find our y value, so we know that v of 0 is equal to -10, and we know v of 60 is equal to 13. Now here is our questionable y value. The y value we're trying to find out is, will we pass through -2? Well, since we have a low y value of -10 and a high y value of 13, to get from -10 to 13, we certainly have to pass through -2. Therefore, the intermediate value theorem says, yes, we will have an x value that produces a y value of -2. So here's my write-up. Since v of t is continuous on the specific closed interval from 0 to 60, and this is how you're going to write this up, this is the expectation. Now I'm going to state my actual y values. V of 0 is -10, v of 0 is 13. Then, by the intermediate value theorem, and you do not have to quote intermediate value theorem, so this part right here could be left off. If you're going to quote the wrong theorem name, leave it off. So there must be a time when the velocity is -2 because, and here's my justification, -2, the questionable y value, is in between the two endpoint y values. Problem or question number 3. Let me move this down a little bit. In number 3, we have another piecewise function. And so for the piecewise function, the first piece, the quadratic or the parabola, is only defined at one specific value of x. So this is just going to generate 1 point. So the first thing we're supposed to do is find f of 4, and then we're supposed to find f of 10. So when we want to find f of 4, we're going to substitute into this piece of the function, because that's where the equal to is. 4 minus 2 is 2, and 2 squared is 4. So I don't know if I wrote that anywhere, but I'll go ahead and write it. So f of 4 is equal to 4. And then f of 10 is defined for the second piece. And so when x is 10, y is 5. Does the intermediate value theorem on the closed interval from 4 to 10 guarantee a y value u such that the u, in this case is the y value, is between f of 4 and f of 10, why or why not? Sketch the graph of f of x for added visual proof. All right, so here's the graph that is produced. There's the solid point that when x is 4, y is 2. And then when you substitute 4 into the second piece, you get a y value of 5. That's going to have a hole in it. And there's a hole at, a solid at x equal to 10. The intermediate value theorem does not guarantee a value on the closed interval from 4 to 10 such that f of 4 produces so that u is a y value between f of 4 and f of 10, or we could say between 4 and 5, because f of x is not continuous on the closed interval from 4 to 10. There's a discontinuity right here. All right, let's go on to number 4. In number 4, f and g are continuous functions. So you got to learn to start looking for these clues right here. So they're already setting us up for something. We have a continuous function. F of 3 is 5, and then they give us some limit information. Find g of 3. All right, so this limit information is on these mysterious f and g functions, and what I ultimately want to find is g of 3, so my only connection to g is right there. And I know that the limit as x approaches 3 is equal to 4. All right, so I'm going to begin by taking that second statement where they tell me that the limit as x approaches 3 of this particular function is equal to 4. Now, since f and g are both continuous functions, and I'm trying to find g of 3, so since both f and g are continuous functions, the limit will equal to the y value. So when I find the limit, I'm going to substitute 3 in place of x and substitute 3 in place of x. So that would give me 2 times f of 3 minus g of 3. I know that f of 3 is 5, and I'm trying to find g of 3. So now it becomes a little one-step equation. 2 times 5 is 10 minus g of 3. And remember, we know that that y value is equal to 4. So I'm going to set that limit equal to, or that y value equal to 4, subtract 10, divide by -1, and therefore g of 3 is a value of 6, which is what I was looking for. In number 5, f of x is continuous. That is important. That means the limit will exist. It's on a closed interval, so IVT might apply. The y value of the first endpoint is 11. The y value of the second endpoint is -11. So without reading any further, I know that I'm going to pass through all y values between and including -11 and 11. Which of the following must, be careful with these kinds of questions, multiple choice, must be true, not could be, but must be true. All right, so let me erase a little bit here and get this stuff out of my way. So the first statement is f of 0 must, so substitute that word, f of 0 must equal to 0. Well, we have really no way of knowing that just because we're going from positive 11 to a negative 11, and it seems like this might be like an odd function maybe. We don't know that it's an odd function because they never told us that it's an odd function. So it could be true, but it doesn't have to be true. So letter B, the limit as x approaches 2 on the function f of x is equal to 8. I don't really know anything. The only 2 points that I know about are negative 4, 11 and positive 4, negative 11. I really don't know how the graph travels from there. So I don't know that the limit as x approaches 2 has to be 8. Letter C, there is at least one x value between negative 4 and 4 such that the y value must be 8. Now remember, we had a low y value of negative 11 and a high y value of 11. So to go from negative 11 to positive 11, we certainly are going to have to pass through a y value of 8. So C is the answer, and since there's only one answer, there's no need for me to keep reading. Problem number 6. The functions f and g are continuous, there it is again, continuous for all real numbers. The table below gives values of the functions at selected values of x. The function h, so now we have a third function. So we have an f function, we have a g function, and we have an h function. And the h function is comprised of a composition. Remember, composition is when you put one function inside of another. And then we're going to create a vertical shift by adding 2. So here's our table of values. Our job is to explain why there must be a value w, that's a value of x, between 1 and 5. So we're going between 1 and 5. We're not going between 1 and 7. Such that there is a y value, h of w is a y value of 0. Now we know that f and g are both continuous. Therefore, h has to be continuous because h is comprised of f and g. So we already know that h is continuous, and it's going to be continuous on the closed interval from 1 to 5. It's going to be continuous everywhere. All right, so the next thing we need to know then is what are the y values that are produced by each endpoint. So what is h of 1 and what is h of 5? And to find those, I'm going to substitute those into my function, and that's the work that I'm doing here. So h of 1 is equal to g of f of 1, and I'm going to go into the table. F of 1 is 3. Go into the table. G of 3 is negative 10. Negative 10 plus 2 is negative 8. So that's what happens when I substitute substitute 1. Do the same thing again for 5. So f of 5 is 7. G of 7 is 25. 25 and 2 is 27. So those are my endpoint y values. So I have a low of negative 8, a high of 27. Those are my y values. So to get from negative 8 to 27, I obviously have to pass through a y value of 0. Pay careful attention to the write-up. Honestly, you just want to practice and practice and practice that write-up. So I said, since f and g are both continuous everywhere, h is also continuous everywhere, thus continuous specifically, I didn't use the word specifically, but pay attention, on the closed interval from 1 to 5. So I need that declaration there. Now I'm going to name and claim my y values. H of 1 is negative 8, h of 5 is 27, and since zeros between negative 8 and 27, by the intermediate value theorem, remember I said you don't have to name the theorem, so you could leave that out. There must be a value w that generates a y value of 0. All right, let's go on to 7, 8, 9. So number 7, let h of x be a continuous function. So we have another continuous function. We have values of h given in the table. For which value of k will the equation h of x equal to 2/3? In other words, they're saying, when will h of x produce a y value of 2/3? have at least two solutions. So in other words, we want to produce a y value of 2/3 twice. So we have this mysterious function, which means we want, so think about the line, let me draw it over here. We want a function h of x, no, that's ugly. That's ugly too. To pass through a horizontal line of y equal to 2/3. So whatever that graph looks like, we want it to hit 2/3 and come back through to have at least two solutions. That's what that means. H of x is a function. Now, it looks like a parabola here, but I'm not saying it is a parabola. That's just sort of what it might look like on the interval from 2 to 7. All right, so if I come back up here to my table of values, let's change colors. Let's go green now. So h of 2 is right here. H of 2 produces a y value of 2. And h of 7 produces a y value of 3. Now here's the mysterious k value. So in order for this function to have two solutions or hit 2/3 twice, we have to go below 2/3. So in other words, the y value of k has to be some number that's lower than 2/3. Because come back over here and look at this graph. I need to go below 2/3 and then come back up and hit 2/3 a second time. Therefore, the mysterious y value right here needs to be a number that's smaller than 2/3. So I'm going to find common denominators. So this would be, if you don't know your fractions that well, so over here I have 3/4. So I'm going to say the least common denominator between 2/3 and 3/4 would be 12. So this would be multiplied by 4, multiplied by 4. That would be 8/12. And over here, to get to 12ths, I'm going to multiply by 3, multiply by 3, and that would be 9/12. So 9/12 would not go down far enough. We can't just equal 8/12. We have to be less than 8/12. All right, so now I'm going to do 2/3 again, but now I'm changing it into ninths. So if I'm going to change 2/3 into ninths, I'm going to multiply by 3 and multiply by 3, so that'll give me 6/9. And if I look back over here, 7/9 is not going to go below 6/9. 2/3, some people might think 2/3, but that's only going to give you one touch. It's not going to give you two touches. So these are going to be gone. And then finally, I mean, by process of elimination, the 18ths have to be the answer, but we can guarantee it. Change 2/3 into 18ths, multiply by 6, multiply by 6. That's 12/18ths. And look right here. We are finally going to go below 12/18ths to get 11/18ths. And that means we have to go below 2/3 and then back up. And so our graph will have two solutions in that closed interval. Moving on to problem number 8, we have a piecewise function, and this is what we've practiced before, forcing continuity. So we're going to substitute 1 in place of the first piece, and that gives me 1, 2, close circle because of the equal to that you see right here. Substitute 1, and I get a y value of 3 plus a. That is an open circle, so currently my function is not continuous until I make this solid fill up the hole. So the y value 3 plus a has to equal to 2. Therefore, a has to equal to -1, which is b. And then finally, question number 9. Back again, f is a continuous function. Make sure you pay attention to the reading on a closed interval. The y value generated by -3 is -1. The y value generated by 6 is 3. The intermediate value theorem will guarantee, so without looking down, I can tell you that the intermediate value theorem guarantees that we will pass through every y value from -1 to 3. Every y value is going to be included. So, does it guarantee that f of 0 is 0? No. I mean, are we going to pass through 0? Yes, but it might not be a 0, so that's not a guarantee. Does the intermediate value theorem guarantee anything about the slope of the graph? Well, maybe, but I'm going to look elsewhere before I have to deal with that. I know there's only one answer. Letter C. All y values between -1 and 3. Oh, I'm sorry. The function itself, I'm sorry, I didn't read that correctly. The function itself stays in between -1 and 3. Now, let's be careful with that one. So if we plot these points, -3, 1, 2, 3, and -1, and 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, we could have a graph that goes way above 6, or we could have a graph that goes way below -1. So letter C says the graph always stays in between -1 and 3. Well, we can't guarantee that. Letter D says that there will be a y value of 1 at least one time between -3 and 6, and there's your IVT promise, letter D.